Okay, I see that there's lots of discussion about the homework assignment that's due today. That's good. You guys can help each other out. It's always good to work in groups. So are there any questions? I've actually helped several of you with the homework today already, but in my office. But are there any questions about the homework before we forge ahead?
For the first one, when we have x and y, you need to make separate ones for x.
Yes, that's a good question. There was one of the exercises in the book was a switching circuit, and it had 4 inputs and 2 outputs. Well, anytime you have 2 outputs, you have to have a separate circuit for each output. So there should be, you should show 2 4x4 Carnot maps. What was the number of that exercise?
52b.
52b, chapter 10. So for chapter 10, problem with exercise 52, you need 2 4x4 Carnot maps because they're one for the x output and the other for the y output. Okay, well, last time in the lab we did, we really got ahead of the lecture. So now what we'll do is we'll learn, we'll learn what we did in the lab. So at the end of the last lecture, we had just digitized the time axis, right? So we have this clocked SR latch, and the thing that clocks it are these AND gates that the S and the R, are enabled by the CK pulse, by the clock pulse, right? And let's review then what the S and the R do. If S is 0 and R is 0, and a clock pulse comes along, what happens to the state of the flip-flop, of the latch? Let me repeat that. If S is 0 and R is 0, and a clock pulse comes along, what happens to the state of the latch? Trick question, actually. Yeah, it remains unchanged, right? Because if S is 0 and R is 0, it'll keep its state indefinitely. So if S is 0 and R is 0, and then a clock pulse comes along, the state remains unchanged. What happens if S is 1 and R is 0, and a clock pulse comes along? It sets Q to 1, regardless of what it was before.
Unless it was already 1.
Well, it's still 1. Regardless of, in other words, regardless of what it was before, it sets Q to 1. And if S is 0 and R is 1, and a clock pulse comes along, what does that do?
Q is 0.
It forces Q to be 0, regardless of what it was before. And here's the trick question. If S is 1 and R is 1 and a clock pulse comes along, what will happen? It's unpredictable. It is unpredictable. Because what will happen is S and R will be going down together at the exact same time, and it depends on which one wins the race. So it's kind of like, by the way, they call that a race condition. Okay, it's a race condition. It's unpredictable what would happen. Yes, question?
Is there a large variance in the speed of the electricity that's going through?
Well, the question is about the speed at which the signal goes through. A gate delay is on the order of nanoseconds, and that is very slow compared to going along the length of a copper wire without any gates in between. So going along a copper wire, that's practically, for all intents and purposes, that's instantaneous. Okay. Although it's not quite. It's actually not, I say for all practical. There are some, we're getting so fast now to where the length of the wire actually can make a difference. Yeah. It's about, if you're in English, a foot, it's about a nanosecond a foot in a wire. That's the speed of light. The speed of light is about 1 nanosecond per foot. So that's how this implementation is of figure 11.7. And then figure 11.8, we saw that what that does is that forces the transitions to all be very, they're taking place on the rising edge of the clock pulse. That's when the transitions take place here, right? Okay, now Today, we're going to go through a pretty involved explanation with lots of detail about a problem that we have and how we're going to solve it. Now, first thing I have to do is convince you that we have a problem. Houston, we have a problem. Here's our problem, Houston. We have a problem with feedback. Now, here's the thing, you guys. Before we talk about feedback, let's go back to figure 11.7. You see in figure 11.7 that the thing that gives this latch state is the fact that there is some feedback. You see this Q bar feeds back to the input of the top OR gate, and then the Q output of the top feeds back to the other one. So you see that's some feedback. Now what I'm here to tell you is that this is not the feedback we're talking about that's producing the problem. Okay? This feedback is what gives our latch state. It enables it to have state. But I'm talking about another feedback problem. Because here's what we often do. Flip-flops are used in circuits with external feedback. Do you see what I mean? So like, let's go back and look at this figure 11.7a. You see figure 11.7a is the block diagram. Now what's inside that block in figure A? All of these 4 gates are inside that. Are you with me? So internal to that block diagram, there's a little feedback. I'm not talking about that feedback. What I'm talking about is if we have a bunch of flip-flops, each of them with their own little internal feedbacks, there could be some feedback external to those blocks. Are you with me? Is everybody clear? Okay. So flip-flops are often used in circuit with feedback connections in addition to the internal feedback in the latch. Therefore, unstable states are possible. Now, do you remember how the first circuit that we looked at when we had feedback, it was unstable? Do you remember what that circuit looked like?
3 hex inverters.
Yeah, it was 3 hex inverters. And with 3 hex inverters, you know, if there's a 1 on the first, then there's a 0 on the second, then there's a 1 on the third, then there's a 0 on the outside. But then the 0, we started with the fact that there was a 1, and if it feeds back, and what did we say that circuit would do? What did we say that circuit would do with those 3 inverters? What would it do?
Flicker.
Yeah, it would flicker. It would literally go, you know, if you put an oscilloscope, or if you could actually see in time, it would actually go up, down, up, down, up. Actually, that's one way to produce a clock pulse. You think about it. It's a very crude way to do it, but you could do it that way. Is everybody with me on that? All right, and so therefore, and so it would be at any particular point in time, it would be next to impossible to predict whether whether at that point it was a high or a low. Are you with me? So now here, before we go to the last bullet point, let's go to figure 11.9. Here is an example of a circuit that has an SR flip-flop with some feedback. So imagine here, so here's the SR, and this is a sequential circuit. It has state, right? And here we have the clock impulse, the clock line going into this SR latch. And let's just imagine, and over here on the left, we have some input coming from some external source from the circuit. And then we have feedback. Our external feedback, goes from the Q and the Q bar on the output here, and it feeds back into this combinational circuit. Now, you understand, when this box labeled combinational circuit, inside this combinational circuit, there's no what kind of connection? Inside the combinational circuit block, there's no what? What kind of connection? There's no. If it's a combinational circuit, what does it mean? The output does what?
Depends only on the input.
Depends only on the input. So there's no little internal feedbacks in there, right? Are you with me? Because it's a combinational circuit. Because for the combinational circuit, the output depends only on the input. But now wait a minute. We also know from our analysis of combinational circuits that it's just a matter of a few what before the...
Gate delays.
A few gate delays. Are you with me? So after a few gate delays, the output will depend only on the input. Are you with me? And it depends on how many levels of delay there are. But still, after a few gate delays, the output depends only on the input. So now let's think of this scenario. Let's think about this scenario. What if at one point in time we have the input is coming in here, are you with me? And this is a combinational circuit, right? And let's suppose that the input to S is 1 and the input to R is 0 coming out of this combinational circuit. The output of the combinational circuit, which is the input of the flip-flop, is SR equals 1, 0. Now, if SR is 1, 0, then what is Q?
Q is 1.
Q is 1 because that's the set.
Assuming the clock there's a clock pulse.
Well, yeah. Well, actually, let me back up. And let's suppose that the clock is 0. Right? So the clock pulse has not happened yet. And let me actually back up. And if S is 1 and R is 0, it's very possible that Q could be what? 0 and R could be what? Sorry, and Q could be 0 and Q bar could be what? 1. Even if S is 1 and R is 0. Why is that? Because the clock is 0. Are you with me? Mm-hmm. Now imagine this scenario. If that's what we have, imagine this scenario. Now the clock strikes 1. Hickory dickory dock. Now the clock goes up to 1. Now when it goes up to 1, what happens? That does what? Yeah, Q becomes 1, and then what happens? Q bar becomes 0, because S is 1 and R is 1, right? But it could, depending, if you're very unlucky, Murphy's Law, if you're very unlucky, what could this output come around here and do? It could go through this combinational circuit, and a few what? Gate delays later, it might produce what? Different S and R. In fact, instead of S being 1 and R being 0, it could flip around and make what? S0 and R1. Are you with me? And when would that happen? So the clock comes up, and when would it happen? Just a few what? Few little gate delays, right? And then, if you're really unlucky, that would feed back around, and what could happen?
On the next clock pulse, it could change?
No. Not the next clock pulse, but what?
During the same one.
During this same clock pulse. Not the next one, but during this same one. If you, depending on the design of that combinational circuit, that thing could go back and forth, back and forth, back and forth, back and forth. It could, right? Depending on, if you were unlucky, if your design were, and so what could happen is that Q and Q bar could be going 1, 0, Q could be going 0, 1, 0, 1, 0, 1, 0, 1, really, really fast. Every few gate delays, it could be changing. And then, here's what would happen. Then, what would happen then when finally this clock pulse goes down and we come like this? Then, could you predict? Could you predict, if it does a billion transitions here, could you predict which state it would be when it came down? No. You couldn't. I mean, if this was just a little bit longer, it might have made one more transition. You see what I mean? Is everybody with me on what the problem is? See, we have to understand. So before we get into all of this rigmarole about how we're going to solve the problem, we have to understand what the problem is. That's the problem. Are you with me? The problem is just even if this is, even if the clock pulse goes way like this, and these are really skinny, even if it's a real skinny, it could do billions of transitions here, and we'd never know what it was coming down. You see what I'm saying? So what do we want to have happen? In order for us to have it predictable and, being able to design with predictability, What do we want to have happen? Now think about this. What do we want to have happen? As soon as this clock pulse goes up, what do we want to have happen? Well, depending on what S and R is, that should do what? Set the latch, according to our rules, either 0, 0, not change, 1, 0, set it to 1, 0, 1, reset it to 0, blah, 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 right? Right. But not allow what to happen? Not allow what to happen? Well, we're going to have the feedback because that's how our circuit is designed, but
Not allowed to go all the way to S and R.
yeah, not allow it to make another whole loop. Not allow it to loop more than one. You see what I'm saying?
One loop.
In other words, once this Q and Q bar output change, we want to disallow that change from going through the combinational circuit and possibly changing it again.
Wait,
Do you see what we have to do?
yeah, do you do like an enable with the clock, kind of? Like or a disable?
Well, but the clock has got to be so high for, I mean, we can't you might try to like spike the clock and just have it be tiny little width.
No, I mean
And
like,
so short that it wouldn't have time to go around.
on the feedback.
In the combination circuit?
No, right before the combinational circuit. Have it like tap off from the clock and have it be like an enable from,
Actually, what you're saying is pretty close to what we're going to do.
okay.
We are going to tap off the clock in a certain way.
Cool.
Yeah. And but I want everybody to understand. Does everybody understand what we need to have happen? We need to have the first change in the flip-flop, that very first change, we want it to capture that change and not let any feedback, external feedback, go through the combinational circuit and change it again. Are you with me?
Until the clock pulse ends.
No, I mean, period, for that clock pulse, until the next clock pulse comes along.
Oh,
And then when the next clock pulse comes along, then it can do it another operation. But even for that second clock pulse, we want any change to happen just once and not have it loop through and in case it would be unstable and do it again. Is everybody with me on this? Does everybody understand what it is that we have to do?
So, sorry.
Yeah, sure.
This is all because you don't know what the combinational circuit is going to do.
Yes, and in fact, there are many common situations, and you will see them. We will see them in the coming weeks. We will see that, oh, how is it that this could work? Oh, that's right, we solved that problem. In other words, we will see situations where something is going in one and out the other, and in fact, you did it in the lab. I don't know if you might not realize it yet, but yeah, there's many common situations where that's what we want to have happen. In other words, it only goes through, only the first change goes through, and that change is not allowed to loop back and change it again. And of course, that with some combinational circuits it wouldn't matter, but in many of them it does. So we design it this way so that it will work regardless of what that combinational circuit is. Does everybody see? Does everybody understand what we're doing? What the problem is now? Okay, so let's go back here to our last bullet point. There are two design solutions to this feedback problem. One design is called edge-triggered. It's called edge-triggered flip-flop, and the other one is called master-slave flip-flop.
we did that in the lab.
And yeah, you recognize, which one did we do?
Master-slave.
Yeah, we did master, yeah. Actually, the chip that you used in the lab the other day was a JK master-slave flip-flop, yeah. Yeah. So now this is going to be a bit of an involved explanation, but it's really important. It's a really important concept. So here's the concept behind the master-slave flip-flop. Okay, so now the reason it's called the master-slave flip-flop is because the master tells the slave what to do. All right? It's master-slave. So the master tells what happens is the slave follows the master. The master, are you with me? So it's the master-slave flip-flop, all right? And this master-slave principle solves the instability problem caused by possible external feedback. And now, so what, let's take a look, let's jump forward to figure 11.10. So here's a block diagram of the master-slave flip-flop, and look at this complicated circuitry here. We're going to understand every little detail of this in the next few minutes. Okay? So here's the block diagram. The block diagram has S and R coming in from the left, and the clock pulse typically goes in the middle. And then we have Q and Q bar. Q is the top one and Q bar is the bottom one. Okay, so that's the block diagram. And all of these gates, how many? 1, 2, 3, 4, 5, 6, 7, 8, plus an inverter, are all inside that. Is everybody with me on that? And you see that this has three inputs and 2 outputs. There's the 3 inputs in part B, S and R and CK, and the 2 outputs are Q and Q bar. Now look, you guys, what this is. Oh, and by the way, the left one, this one right here, is the master stage, and this one is the slave stage. And you'll see why in a minute. Okay? Now, there's one more, besides this, we know what a NOR gate and an AND gate and an inverter is, so we know how all these gates operate. But there's one more thing that the electrical engineers can do for us, and that is they can adjust the threshold at which a gate switches. Now, so hear me out on this. Let's suppose that you're in the lab and you hook up one of those hex inverters, right? And you put the input on a you have a wire going into the input, and you can plug it into power or ground or something, and you can put the output on a light, right? And typically what we do is we put the input on a switch, yeah? And what did we say, and what did we say the voltage was? Plus 5 volts. And so if the switch is off, that input is at what voltage?
0.
Zero is 0, and if we put the switch on, that input is at 5. And we know that if it's 0, the output is 1, and if the input is at 5 volts, the output is 0, right? Well, actually, let's do this all with voltage. Let's say that when the input is 0 volts, the output is 5 volts, and when the input is 5 volts, the output is 0 volts. Are you with me? But now, instead of having that hooked up to a switch, suppose we have that hooked up to a lever, and we can gradually raise the voltage from 0, the input voltage from 0 to 5. What do you think the light would look like? As we go gradually from 0 to 5, would the light from 0 to 5, would the light start high and gradually go dim? Do you understand what I'm asking? If the input is at 0 volts and we gradually raise it up to 5 volts, then will the output start bright? Would the voltage be high and then gradually go down to 0? Do you think it would?
As opposed to it being completely dark
And then flipping somewhere in between to dark. What do you think it would do? The way these things are designed, they're designed to be what? To either be what? All what? All on or all off. So what do you think it would do, just physically?
Just wait until it gets enough signal and then turn on.
That's exactly what it would do. It would not be gradual. It would flip at a particular voltage. Are you with me on this? Yeah? And what do you think where do you think the threshold is? In other words, the output is at 5 volts, the input is at 0 volts. And then if you gradually move it up from 0 to 5, what do you think they normally design the threshold?
2.5.
2.5. Why? Because that's right in the middle. And so what would happen then is if you gradually increase it from 0, and once it gets to 2.5, all of a sudden, bloop, it would flip. The output would flip off. Are you with me? The voltage at which that transition happens is called the threshold voltage. And guess what the engineers can do? The electrical engineers can do for us. They can design that threshold to be whatever they want. Are you with me? And so one additional factor that makes this work is these two AND gates of the master, the enable AND gates of the master, they are designed with a threshold V2, which is not just halfway in between. Instead, it's higher than normal. And furthermore, they can design the threshold of this inverter down here with the threshold V1, which is what? Lower than halfway. Are you with me on this? Is everybody clear on this? So what would happen then is, and now here's another fact. Nothing in nature happens instantaneously. So the clock pulse, even though we typically draw it on our timing diagrams in the lab as being square like that, really, if you take a look and zoom in on it, on the time scale, really what does it do? It doesn't go immediately up. What does it do? It goes, so if this is the clock, what does it do? It goes like this. Are you with me? And then when it goes down, really it doesn't go straight down. Really, what does it do? It goes down like this. Are you with me? Yeah? And furthermore, suppose the clock is 0 over here, or right here, suppose the clock is 0. As it gradually goes up, what's going to happen? If this V1, so now,
Lower than V2.
is low, if this V1 is lower than V2, then what happens is this. So if this is V1, and this is V2, then tell me, what's going to flip first? Yeah, the inverter is going to flip when? Before V2. Before the S and R get through. Are you with me? And not only that, on the way down, what's going to happen? The S and the R are going to do what? Their outputs are going to do what?
They're going to finish.
Are going to flip, before V1.
Right.
So the fact that this is not instantaneous and that V1 is less than V2 defines 4 different times. All right? T0, T1, T2, T1, T2, T3, and T4. So this is time T1, this is time T2, this is time T3, and this is time T4. Okay? And there's actually a picture of this on figure 11.11. Everybody see what this is? T1, T2, T3, T4. And that's the time. And so we have these 4 times when these events happen. And let's go back now then and look at what the implications of this for the operation of this circuit. Now, so first let's see what happens before when the clock pulses when the clock is at 0. When the clock is at 0, tell me, if the clock is 0, is this SR getting in to change, can the SR change the state of the master? It can't. Why not? Because if the clock is 0, it's enabled with these AND gates. So does everybody understand? When the clock is 0, the S and the R are blocked from changing this, right?
It's because S and R would both be 0. Because of the AND.
Yes, because of the AND gate, they'd be zeros. Yeah, and so whatever state this is in, it's unchanged. Are you with me? It's unchanged. And now tell me, so what state could it be in? It's either going to be in, so now there's only two possible states that that the master latch can be in. It can either be in what? Yeah, well, if this is 1, then this must be what? 0, right? On the other hand, if this is 1 and this is 0, tell me, what's going to be the state here? Well, if the clock is 0, now follow me through here. If the clock is 0, then what's on the other side of this inverter? 1, which means that what's happening here? This is going through. And so if this is 1, this has to be what? If this is 1, this has to be 0. And what does this have to be? This has to be 1. Are you with me? Is everybody clear? So basically what we're saying is that the master is connected to the slave. The slave is following what the master does. Yeah?
But it isn't right now.
Well, I mean, it's always the opposite. I mean, but it's following it, all right? And furthermore, and what's the other possibility? Of course, the other possibility is that what? Is that the master state is what? What did we have before? We had a 1 here?
Yeah, so 0 now.
Yeah, so if this is 0 and this is 1, then this one goes through this and forces this to be what? 0 and forces this to be 1. Are you with me? So what we're saying then is that the master is connected to the slave at that point. Is everybody with me? The master, or maybe you can say it the other way around. The slave is connected to the master, right? Now, watch this. Now there's 4 events are going to happen on the way up, 2 events on the way up, and 2 events on the way down. So what happens now when the clock pulse comes along and we hit V1 at time T1? What happens when we hit V1 at time T1? So this is coming up, right? The clock is coming up. Well, do you see then that this is going to flip before this? And what's the output? So this V1 is going to flip. This is 0. Now this V1 is going to become what?
1.
This V1 is going to become 1. All right? And what is this?
That's what we just did.
Sorry, wait. No. The clock is 0 and this is 1, right? So when it comes up, as this is coming up, this is going to flip to what? This is going to flip to 0 as we're coming up. Do you see what I'm saying?
Is 1 then?
No, what? Hold on. So this is going to flip to 0, right? At time T1. Now when this flips to 0, what's that going to do?
0, 0.
That's going to disable this.
that's
So
gonna
now
disable
nothing coming in here can do what?
change the state.
Can change the state here.
0, 0 is
Because the 0, 0s are coming out here. Ah. Did everybody hear that? Are you with me? So, are you with me? So when this flip, the clock is on the way to 1. Well, the clock is on the way to 1. Well, this flips to 0 at this time T1. All right? And what that does is that uncouples the master from the slave, right? Because now on the other side of these AND gates we have zeros, and so this state will not change. And then what happens at V2, at time V2? Now what happens at time V2? Now what happens at time? At time T2 when we get to level V2? These gates do what? They open up, right? Because that's when this one flips. That's the threshold. And so these gates open up, and what do they allow to happen? What do they allow to happen? This S and R from outside now can get through to what? Wait, no, not to the slave. This S and R can get through to the what?
The latch, the first latch.
to the first latch. And that might do what?
Change that.
That might change this. But wait a minute.
It's still V2.
But wait a minute. That changes this. Can this immediately get through here?
No.
No, why not?
Has to wait.
Because at time t1, that was disabled. Are you with me? Yeah? Does everybody see how that worked? And do you see how that's going to solve the problem? Because look, on the way down, it's just the opposite. On the way down, what happens first? Yeah, this is disabled, so anything coming in here, anything coming in through this SR, this external SR, can't do what? Can't change this. But then at time t4, what's going to happen? This 0 is going to flip up to what? To 1, and all of a sudden, what's going to happen? Q and Q bar, they might change. But look, if there's feedback, external feedback that comes from here all the way down to here, is that going to go through? Is it going to go through? No, why not? Because this is disabled from this. Now, you guys, look. It's like this. There's a really accurate analogy for what this is doing. So you guys know, like if you're in a submarine or if you're in the last time you were on a space shuttle mission,
Right.
and you want to do a spacewalk, what do you have to do to get outside? What do you have to go through?
Air chamber.
You have to go through a compression chamber, an air chamber. Yeah? And so think of it as two doors being closed, right? And say, here you're in the space shuttle and here's outer space. So you put on your spacesuit, right? And what do? Both doors are closed, right? You open this door. Right? And then you get in to the compression chamber, and do you just open this door? No, what do? You close the first door, right? And then you open the second door, and then you can get out. Now, what would happen if you open both doors at the same time? Well, the air would go, it would get through. So what you do is it's like this. So what do? You open and then close and then open and then close. Open, close, open, close, right? And that prevents open, close, open, close. So that's exactly what this is doing. Open. Are you with me? Open, open, close. Wait. Yes. It's the same thing. In other words, you don't want to have what? We never have what? We never have these two gates doing what? These are the doors.
Both enabled.
We never have them both enabled at the same time. They're never enabled at the same time. Are you with me? See, between time t2 and t3, which one is enabled?
V2.
Between time t2 and t3,
The master.
yes, this can get in and affect this. That from the outside can get into the master and affect that. But at that point, this gate is closed. So that can't go through here at the same time. That's like the air. The air, it stops there, right? And then between T3 and T4, then at T3, then what we do is we close this gate and we open this gate, and then what was there can get out, but it can't go all the way around and get back in again. So it limits it to just one transition. So here's the terminology, the timing detail of a single clock pulse. At time T1, we isolate the slave from the master. Okay, so T1, we isolate the slave from the master. Now, why does that isolate the slave from the master? Because that flips this to 0, right? And then at T2, what happens? We connect the master to the what? To the input. Are you with me? And then at time T3, we isolate the master from the input, and then at time T4, we connect the slave to the master. And that solves our feedback problem. But now here's one more thing that we have to be aware of. Once we do this, once we have a JK master-slave flip-flop, where do the transitions appear? In other words, when this clock pulse comes along, where do we see the change in the output of the whole chip? Where do we see that? On the rising edge of the clock pulse or the falling edge of the clock pulse?
Falling edge.
On the falling edge of the clock pulse. So now if you look at this timing diagram in figure 11.12, notice that you have to be very careful about this. Notice that it's on the falling edge of the clock pulse that the Q changes. If S is 1 and R is 0 and you send a clock pulse along, notice that the transition now is on the falling edge of the clock pulse. Does everybody see how that works? So now, edge-triggered, it's common. Both techniques are common, but edge-triggered is also quite common, but it's a little bit more difficult to understand. It's kind of tricky, but so I just chose. But you should be aware that there's these two different ways to solve the same problem. Okay, is everybody any questions about this? All right, now. So with that in mind, and now what we're going to do is from now that we've gone through this torturous explanation of what happens and how it works, what we're going to do from now on is we're going to assume that all of our flip-flops are master-slave so we don't have to worry about feedback, right? And I guarantee you there's going to be a time, sometime in the future, when you're going to say, but wait a minute, won't that? And then I'll say, aha, but remember, this is designed with master-slave principle, and so it'll work, see? So now let's take a look. So now what we're going to do next is we're going to look at how to design different sequential circuits using flip-flops designed with this master-slave principle. And the first thing that we need to think about is what's the characteristics of a combinational circuit?
Output depends only on the input.
The output depends only on the input. So in order for us to describe the operation of a sequential circuit, can we just use a truth table? Yes or no? We cannot. Are you with me?
The outputs change.
Well, because it doesn't depend only on the input. The output doesn't depend only on the input. So what do we use? We don't use a truth table anymore. We can't. So we use what is called a characteristic table. And now what we have to do is we have to think about what happens when a clock pulse comes along. What is the current state and what is the next state when a clock pulse comes? Are you with me? So what the characteristic table tells us is, given the inputs at time t and the state at time t0, the characteristic table shows the state at time t plus 1, that is after one clock pulse. So here is an example, figure 11.3. This is the characteristic table for the SR flip-flop. So let's see if we can understand it. What we're going to do here is the way we're going to notate this, because we've digitized the time axis, we're going to say S parentheses t, that's the input S at time t. Similarly, this is the input R at time t, and this is the output, this is the state at time t. And then we're going to say what happens if S has this value and R has this value and the state has this value and a clock pulse comes along, what will be the state after the clock pulse? And so we're going to indicate that as Q at time t plus 1. And we always know that Q bar would be the same thing as Q except for it's the inverse, right? So, check it out. We have 0, 0, 0. For S, R, and Q, we have all these combinations. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, right? So if S and R are both 0 and the clock pulse comes along,
Nothing happens.
nothing happens. In other words, if Q at time t is 0, then Q at time t plus 1 is 0, and if Q at time t is 1, Q at time t plus 1 is 1, right? So does everybody see that this is not a truth table anymore? It's a characteristic table because we have time t and time t plus 1 with a clock pulse coming along. Are you with me? And then if SR is 0, 1, R means what? The letter R means reset. So regardless of what the initial state was, whether it's 0 or 1, the state Q at time t plus 1 is 0 afterwards. Are you with me? And then at time, or if S is 1 and R is 0 at time t, doesn't matter what Q is at time t, what is Q at time t plus 1? 1. And if they're both 1, then that state is undefined. Now, this looks suspiciously like, you remember from computer systems whenever we did state transition diagrams? This looks like a what? A state transition table, right? So how did we write the diagram? How should we write the state transition diagram?
Table?
No. This is the table. How do we write the diagram? How do we draw the diagram?
Like edges, like a graph?
A graph?
Diagraph?
Yes, a digraph, exactly. And what is it going to look like? Here, can you tell me?
Like a,
Like if we are, here, let's take this table. Look. Here.
like a finite
Here.
machine?
Yeah, it is a finite state machine. If here, there's two possible states, right? 0 and 1.
So then we draw the transitions.
Yeah, so how do we notate the transitions? If the input, now by the input we mean SR. Okay, so input SR. So if we're in state 0 and the input is 0, 0, what does it do?
Loops.
It goes onto itself. Are you with me? So that's input 0, 0. Right? If we're in state 0 and the input is 0, 1, what happens?
Stays 0, 1.
Oh, it stays the same. If we're in this state and it's what?
1, 0.
1, 0,
Then
it goes to what?
To 1.
Are we good?
And 1, 1, you're just not going to draw that one.
And 1, 1, it's undefined, so we don't have a transition on 1, 1 because it's undefined. Okay, and now if we're in state 1, what happens?
It self-loops on 0, 0 and 1, 0.
It self-loops on 0, 0 because 0, 0 stays the same, and then 1, 0 is the set condition, so that sets it to 1, but it's already 1. And then what?
On reset, it goes back on 0, 1.
On reset, it goes back to 0.
Cool.
Yeah, and so here it is. That's the state transition diagram. And guess what, you guys? When we do sequential design, our sequential designs are all going to be specified by these finite state machines, state transition diagrams.
Cool.
So see, finite state machines not only for parsing and stuff like that, also for, at the hardware level with sequential circuits. And the transitions happen at each clock pulse. All right, good deal. See you next time.